Hello everyone, let's look at Leetcode question 543, diameter of binary tree. At the time of recording, this question has 13,000 upvotes and 856 downvotes. The question is, given the root of a binary tree, return the length of the diameter of the tree. The diameter of a binary tree is the length of the longest path between any two nodes in a tree. This path may or may not pass through the root. The length of a path between two nodes is represented by the number of edges between them. In the first example, we have this binary tree here, and you could see starting at 4, 2, 1, 3 would be the longest path. So we would return 3, as it's 3 steps to get there. Also, you can consider 5, 2, 1, 3, that's also 3. And let's look at the constraints before going into depth. The number of nodes in the tree is in the range between 1 and 10,000 nodes, and the values of each node are between -100 and 100. Okay, so for this question, we define the depth first search node value, and we call it with the depth first search root initial value, which is 1 in this example. We also define the self.max diameter. We need to use the syntax self.max diameter because we need multiple instances for the recursive calls and to keep track of the updated max diameter. So before going into this example, let's run through this depth first search function, and we check first if the node is none, in which case we return 0. And then we go left depth and right depth and check the depth first search for the leftmost and rightmost nodes. So we keep splitting up every node starting at the initial one until we reach the very bottom, the child, the leafed nodes, the bottommost leaf node. And then we can update the max diameter by checking which one is greater, the max diameter or the left and right depth added together. And we add these together to create the path of left and right. And this will define another diameter. And then we return simply the max left and right depth, whichever one's greater, and add 1 to it in order to iterate back up to the previous node and add 1 to the depth of the current node. Okay, so let's loop through this example. Okay, so what we're going to do is first define the self.max diameter to be 0, and we do the depth first search call on the root value, that's 1. And we go to the function call then, depth first search node value is 1, and we check if node is none. It's not none, it's 1, so we skip that. And when you do these recursive calls, the left and right depth, for depth first search node.left and depth first search node.right. Okay, so we create new instances of the node calls for the left and right values. Okay, so then let's look at 2, and the same thing is happening. We check if node is none. It's not none. So we define left depth to be a new instance, depth first search node.left, that's 4. And a new instance node.right of 2, that's 5. Okay, so we once more do the same thing for 4 and 5 and for 3 also. But since 3 is higher up, we'll do 4 and 5 first. Okay, so 4 is once more called in a new instance for depth first search. If node 4 is none, it's not none, we do the next thing. So left depth, node.left, right depth, node.right. Same for 5. The same thing's happening between 4, 5, and 3. And as you can see, there is none on all calls to left and right nodes for 4, 5, and 3. So what does this mean? Well, what's happening is that we are now returning 0 for these node values. So 4 to the left, we call this node and we say if node is none, return 0. So 0 is being returned for left and 0 is being returned for right for both 4 and 5, these two nodes, okay, and 3. So then we do finally the self.max diameter call because we have arrived at our base case where we can finally return 0. So we go back up the recursive ladder for 4, 5, and 3, and we say, okay, now that left and right depth are defined, for the node 4, we define what max self.max diameter is, and that's currently 0, and we add the left and right depth, that's 0 plus 0, so this max depth is still going to be 0. Okay, but then we return 1 plus max of left and right depth, so 1 plus 0, that returns 1. So 1 is returned for 4, so 1 plus 1, and 1 is returned for 5, that's also plus 1, and 3, there's a same thing, so it's also going to be adding 1, we're returning 1 for this return 1 plus max left depth and right depth. And as we defined, they are zeros because the left and right nodes are none. Okay, so we've gone up the recursive ladder, and now for 2, we say the same thing. Okay, what is the left depth? Well, we returned 1 for left, so it's 1 now. And for the right depth, we also returned 1, so the right depth is 1. So we now define what the max diameter is once more. So the max is either 0 or 1 plus 1, that's 2. So self.max diameter becomes 2. And this makes sense because if we take the path from 4, 2 to 5, that's 2 steps. 4 to 2 is 1, and 2 to 5 is another 1, so that's 2. And now we can return 1 plus max left depth plus right depth, okay? So this makes it once more up the ladder of the recursive calls, and this is plus 1 plus the max of left depth and right depth. So what is that? Left depth is 1, right depth is 1, so that's 2. 1 plus 1 is 2. And on the right side, we said it was plus 1 again, so finally we arrive once more at our node root value 1, because we are arriving at the last initial call, so it's going to be now defined as the left depth, which returns 2, and the right depth, which returns 1. And we define the max diameter then, so the max is either going to be 2 or 2 plus 1. So, which is greater? 3. Okay, so self.max diameter is 3. Okay, and this final function, it says return 1 plus max left depth plus right depth. Okay, so clearly the greatest depth is the left one, so it's 2. 2 plus 1 is 3, so we return 3. Okay, and this is the self.max diameter. This is the final answer. And this makes sense because as you can see, the path from 4, 2, 1 to 3 is 3. 1, 2, 3. Or also the path from 5, 2, 1, 3 is also 3. 5, 2, 1, 3. Okay, let's check the solution. Very nice, so it works. The time complexity of this solution is O of n, because using the depth first search, we visit every node once in the tree, resulting in O of n time complexity. The space complexity is O of h, where h is the height of the binary tree, because the maximum depth in a recursion stack is equal to the height of a tree, in the worst case. Okay, so that's it for this problem. Thank you for watching.